Okay, hello everyone. Welcome back to your CompuThread 35 tutorial. So maybe some quick comments before we get started. Well, first of all, okay, so someone said hello, so that means you can hear me. So first of all, just to let you know, assignment 1 marks have been posted. So if you have any concerns or comments about the grading, like I said last time, you can email both me and the other TA, and then depending on who marked your assignment, they'll give you the answer to your question or your comment. The other comment is that assignment 2 is due in less than 2 hours. So hopefully that's submitted or almost submitted. So that's for that. Then the other thing was I was talking about midterm reviews on Monday. So my intention, I just need to confirm this with the professor, is to have a midterm review on Friday from 4 to 5 p.m. So I'll probably do 30 minutes worth of prepared questions. And then the rest will just be Q&A. I just need to check that it's okay if I schedule it with the professor, but I probably think it is. So then if you want to join, feel free, and I'll probably also record it. So there's that. Okay. Okay, good. So that was for little quick announcements. So now let's actually, if there are no questions, we can get into the actual tutorial material. So what is this tutorial going to be about? I'm going to quickly introduce grammars, which were talked about during Monday's lecture and the lecture before that. And then I'll also talk about regular grammars. So there should also be a mention of regular grammars in here. And then we'll also talk about how do grammars and FAs, how are grammars and FAs connected? So yeah, for all, as far as I know, grammars are most probably included in the midterm. So this is probably not a waste of time. So if you're here, then it's probably good. But of course, to confirm, you should obviously, as someone said, ask the professor. But typically, grammars are on the midterm for the summer semester. All right, so introduction to grammar. So what is a grammar? A grammar, it's very different conceptually from a regular expression and from an FA. It's actually a device that generates languages. So you're going to hear that term a lot, that grammars generate languages. So we're going to see how in a second. But if we want a very formal definition of a grammar, then we can think of it as being a 4-tuple. So a tuple of 4 elements where the elements are V. So V is a finite set of variables, which are typically uppercase. T is another finite set of terminals. So this is typically related to your alphabet. Typically the alphabet over which your language is defined is the same as your set of terminals. S is the unique starting variable. So that's one very important thing to note, is that the starting variable is unique, similarly to how the initial state in an FA is unique. So you always start from the same place in a grammar and an FA. And lastly, the most important part of a grammar are actually the rules that allow you to generate strings, and that's the set P of productions, so the set of productions. So even further in terms of production. So what do those look like? Typically, a production, well, always a production will look like X gives you, or so usually I read this gives you, X gives you Y, where for now you can ignore this. For the purposes of regular grammars and the grammars that we're going to look at in this tutorial, we only will see X is a variable. But in the future, you're going to see that grammars exist where in X, there can both be multiple variables and multiple terminals intertwined between each other. But for now, for regular grammars and for the purposes of this discussion, you can just think of X as being a variable, even though that's not the most general case. So the left-hand side is a variable, and the right-hand side is any possible permutation of terminals and variables which are defined here. Okay, so for example, suppose you have the set of variables SAB, the set of terminals AB, and the start variable S. Then the production rules for this grammar are the actual mechanism that generate languages, and they look like this, right? So how would you read this? You would just say, to create or to generate a string, I would start at my start variable S. So let's say I start at my start variable S. Then each step or each move in your grammar is like a substitution. So S can be substituted by A or lambda, meaning that S can just be replaced by lambda, meaning that you could say that your grammar G, so G generates the string lambda. What could also happen is you could say S is replaced by A using this production rule, and then you could say that A is replaced by this production rule, so by B, 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 A. And then now I'm going to use this production rule to replace B. So I could say that B gets replaced by, let's say, lambda. And then I get B, B, lambda, A, and that would give me B, B, A. So another string that's generated by G is BBA. Okay. So maybe a bit more sort of theory on the concepts related to grammars is, like I just showed here, if it's possible to start from X, so to start from the left-hand side, and then using a bunch of intermediary production rules, get to a string Y, then we say that X derives Y, or you can also say that X with 0 more moves gives you, or 0 more substitutions or production rules gives you Y. Okay, so that's what we mean when we say X derives Y. So like I showed here, another derivation that you could get, another string that you could get from this grammar here would be the following. So you could start with S, then you would replace S with A, or you could say that S derives A, right? Then using this production rule, A derives BBBA, and then using this production rule to substitute the B here, I could get that B derives little b, and so altogether I could say that S derives the string BBBA. Okay. So that's how a grammar works. What's the actual purpose of a grammar? So like I said before, the purpose of a grammar is to generate a language. And so we define the language generated by grammar G, L of G, as the set of all strings over the terminals, right? Because your strings that are generated by G can only have terminals from your set of terminals, right? So if T was AB, then all of the strings generated by the grammar G would only have A's and B's. So it couldn't have anything else, right? So we define the set of strings or the language generated by G as all of the strings over the universal or over the set of all strings T star, such that you can start at S and derive your way through production roles to W. Okay. So maybe let me take that question now. Can you apply the production rules in any order? You can apply any production rule that starts, like for instance, if you have S, you can apply any production rule that starts from S and goes to the right-hand side. So you could do SA, you could do S lambda. So it doesn't matter if you start with A or lambda, right? But of course, if you do S gives you lambda, then you can't go forward. You can't go to another variable, right? But if you do S gives you A, then you can go to this next set of productions. Okay? So the order only matters in what you can produce, but you're free to use any order you want to sort of derive something starting from a particular variable. Okay. So with that being said, so maybe it's not clear so far. So let's look at the example that we've been looking at so far more in depth. So we have again the same grammar with the same set of production rules, and now I want to know what L of G is. Okay. So in general, it's not that easy to know what L of G is. In this case, we're lucky because L of G is actually going to be finite. So there's going to be a finite number of strings that can be generated by G. So what are they? Well, I have already showed you S derives lambda, right? So that's clear by just substituting S with lambda. And I can also get little a by starting with S, because notice I always start with S because that's the start variable. So I start with I start with S, replace it with A, and then replace variable A with terminal A. And so a little a or terminal A is another string that's generated by the grammar. Okay. Then another possible derivation and the third possible derivation is this one, which I already showed, which gives you the string BBA. And then the last one is another derivation where instead of using B is replaced by lambda, I use B is replaced by terminal B. And so that gives me that S derives B cube A, right? So here I have a finite number of strings that are generated. So L of G is that set of strings. Okay? So that's how you kind of reason and think about grammars. That's how you kind of navigate them. So far, we've been looking at finite grammars, right? In the sense that grammars that generate a finite language. So now let's look at a grammar that generates an infinite language, so a language with an infinite number of strings. Okay, so suppose we have the following grammar here, which in fact, here it says that the set of variables is SAB, but as you can kind of tell here, A is kind of useless, so that shouldn't even be there because it's never used. So really the grammar is the set of variables is SB, the set of terminals is AB, my start variable is S, so I know that I have to start here, and this is my set of production rules. Okay. So what are the possible strings that can be derived by this grammar? Well, for sure, I can start with S, and then I can give myself lambda, right? So I can start from S and derive lambda. Okay, so that's the easiest derivation that I can see. Or what I could also do is take this path. So I could say S goes to variable B terminal B, right? So I can take this path, and then from here, you can kind of see why this grammar is going to be able to generate an infinite number of strings. That's because I can use this production rule any number of times, because each time I use it, I have a variable B that I can then reuse these productions for. Okay, so that's why I can already see that this is going to generate an infinite language. Okay, so in this case, I have S gives me variable B terminal B, And then here I choose to replace the variable b by a lambda, and so I get b as my string. But what I could have also done is s gives me the variable b, the terminal b, and then again use the same production rule to again give myself another b. And then replacing that b, I can, using the rule b gives me lambda, I can get a b cubed, or 3 b's in a row, right? And so that can continue, right? I can, every time I see a b, I can actually use this production rule. And what's actually going on is that so my initial string is always going to have one b. If it's not lambda, my string is going to have one b. And then for each production rule I use, I'm going to add on an extra 2 b's, right? Because the only production rule that can repeat in this case is bb. So bb is going to be able to add itself multiple times. So every time I do that, I start with a single b and then I add pairs of b's, meaning that the number of b's in my string is going to be 1 plus 2n, where n is the number of pairs of b, okay? And so that means that my string is going to have an odd length, right? So that's why here, the language generated by b is the empty string union the set of strings where those strings are a sequence of b's, and that sequence of b's has an odd length, okay? So that's how you derive this type of grammar, okay? So the next one we'll see is going to be slightly different, okay? But before we look at the next example, we're going to quickly talk about a very important concept, which will lead us to regular grammars, which is the notion of a linear grammar. So before looking at left linear or right linear, a grammar in general is linear if every production rule, so for every production rule P, you have that P gives you something on the left and then something on the right, where on the right you have at most come on, there we go, at most one variable. Okay, so it's very similar to linear equations. In a linear equation, you have a single variable x. In a linear grammar, all of your production rules have at most one variable. So at most one capital, right? So something like, let's say S gives you a S, a B, or a lambda. So this is, and we'll see what this does. This is a linear grammar. But if I have something like S gives me a S or a lambda, then this is not linear. So this is not linear, and this is linear, right? But remember, I haven't talked about sort of left linear or right linear yet. So yeah, so at most one variable, right? So that could be either 0 or 1. So every production rule on the right-hand side has at most one variable, meaning it's either 0 or 1. Okay, so that's what a linear grammar is. Okay, so that's what a linear grammar is, right? So now, what's a left linear grammar and what's a right linear grammar? A left linear grammar is a linear grammar where all of the variables in all of your production rules, if you have a variable, then it has to be the leftmost element in the left hand, in the right hand side of your derivation. Okay, so all of your variables on the right hand side need to be at the left. Okay, and if you don't have any variables, then you should just have a string of terminals. Okay, so if I have something like S gives me SA SB, or A, right, then all of the production rules look like either this or this, because for the production rules that have variables, so these two, the variable, there's only one variable, there's at most one variable, and that variable is the leftmost, a part of the right-hand side. And for all of the production rules that don't have variables, so for instance, this one, it's just a string of terminals. So in this case, just A. So this is linear and left. So not only is it linear, it's left linear. Okay. So that's what left linear means. Then what is a right linear grammar? So a right linear grammar is almost the same idea, except that on your right-hand side, when you have at most one variable, that variable has to be the rightmost element of your right-hand side. Okay, so if you have something like S, AS, or BBB, actually just for a change, let's say you have AB. So you have some terminals, and then you have a single variable, and that variable is on the right. Okay, so this respects this rule. Here, X, by the way, X is just a string of any number of terminals. Okay, that's why it's T star. Okay, so so that's why here this production rule respects this form, and this production rule respects this form. So that means that it is right linear. Okay, so then how does this relate to a regular grammar? Well, a regular grammar, so grammar G is regular if it is either right linear or left linear. Okay, so now maybe a question for you is, if you're given a grammar G, can the grammar G be both left linear and right linear? So maybe he already asked you this question. If that's the case, then you should know the answer. But if it's not, okay, so it doesn't look like, so can a grammar be both left linear and right linear?
Yes.
Okay, someone says yes, and someone says, okay, good, okay. So, so the answer is actually yes. The reason why this is possible is because we're talking about linear grammars. So we have at most one variable, and so if we have at most one variable and we don't have any terminals, then that could be a grammar that's both left linear and right linear. So for example, if I have S gives you A, and then A gives you little a, then this is left linear and right linear, so clearly it's regular. Or you could also just have S gives you lambda, right? So the grammar that generates the language lambda. And this is because this, right? So this production rule respects this, and it also respects this. So that means that, again, here it's left linear and right. Okay, so yes, it's possible. But of course, here you only need the grammar to be either one for it to be regular. Okay? So now let's look at an example of a grammar which we're going to see is regular and in fact right linear. So suppose we have the grammar with this set of variables terminals, and the start variable is S, and we have these production rules P. Okay. Then, well, is it linear? You can just quickly check that it's linear by checking that for each production rule you have at most one variable, right? So this one doesn't have any, the lambda one doesn't have any. So yes, it has, each production rule has at most one variable. So it's definitely linear. Now, is it either left linear or right linear? Well, I see that all of my production rules look like a string, right? So a string over T star or over T, and then a variable, right? So they all look like that, right? So this one looks like that, this one looks like that, this one looks like that, these look like that. And this one doesn't look like a string and then a variable. It's just a string. But if we look at the definition of a right linear grammar, all of the production rules satisfy either one of these two rules or either one of these two conditions. And so altogether, this grammar is not only linear, but right linear. And so because it's right linear, this grammar is regular. And the nice thing about regular grammars is that they're typically a lot easier to determine what the language that they generate is, okay? Just because your variable is always placed at the same place, so always at the rightmost or always at the leftmost, so you can always predict how your next production rule is going to behave, so how your next substitution is going to behave. So for instance, in this case, this grammar is going to generate any string of the form a string, AB, and then a string. So in fact, this grammar is going to generate all the strings that have AB as a substring. And the way you can see that is from the start variable s, right? So from the start variable s, I can produce any string over AB by using these two production rules. So any string that you can think of, I can produce with S gives me AS and S gives me BS, right? So how can I do that? I can just say, let's say I wanted the string AA, BA, right? So I could just continuously replace either A or B. So I could replace S with AS, then this other S with AAS, then this other S with AABS, and then this other S with AABAS. So this can go on forever, and I can keep replacing S with either A or B, right? I'm kind of just doing it one by one symbol at a time. And because the start variable has production rules for all of the terminals, so for the terminals A and B, I can produce any string that's over A and B, okay? So, but the problem is I can never finish this production rule, right? I can never get to a string. I can never get to just a string of terminals because none of these production rules are just terminals, right? So what that means is that at some point, I'm going to have to go through ABA. So at some point, at some production rule, I'm going to go through ABA. So this could be any string W1 over T star, right, over AB star. Then at some point, I'm going to have this string W1 ABA, right? And then at that point, when I'm at A, I can either stop my string or I can keep going. And then I can keep going for any number of symbols over AB. So I can have a string that's over AB and it can be anything that I want by the same logic as this, right? So I have W1, I have ABA. Now I can use the production rule to replace A any number of times with either A or B, right? So I can replace A with, so let's say I have W1, AB, then I can replace it with AA, and then so on. So then at some point, I'm going to be left off with W1, AB, W2, A. So let's say this was either A or B, I don't really care. Then what I can do is I can replace this capital A with lambda, so I can get W1, AB, W2. Okay, and so any string that has a substring AB is going to be can be generated by this grammar. Okay, so that's why this is the language generated by G. Okay, so okay, so maybe actually let's already go to the exercise and then I'll come back to this slide, just because I've been doing a lot of talking. So let's do this exercise. I'll give you a minute. Write a regular grammar, so either a grammar that's left linear or right linear that generates this language, which would be very familiar. So I'll give you 1 minute to try this, and then I'll do the solution and then look back at this example. Okay. Okay, so hopefully you've had the time to at least think a bit about this question. So the idea is we want to create a grammar that generates the language where all of the strings of that language have an even length, right? So suppose you have a string W that has an even length. So let's say A, B, B, A, right? And the idea is that you want to be able to generate this string. So what's the idea? I feel like most of you would have probably guessed what the idea is. It's to generate the string by pairs, right? So because I know that if I'm always adding pairs and I'm ending with lambda, then that means that I'm always going to have, as long as I'm producing, I'm always going to have an even length, right? So I can produce the AB as a pair, I can produce the BA as another pair, and I can produce, in fact, I should have a rule that can produce any possible pair over AB, right? So it's very similar to kind of a regular expression in that sense, right? So we're looking at every possible pair over AB. So what could we have? Well, of course, we could have AB, we could have BA, we could have AA, and we could have BB, right? So how could we create a grammar that generates this language? Well, you could say that your grammar is G, where in this case, let's say that we're only going to need our start variable S. Our terminals are AB. So our start variable is S. And then we have production rules P. And the production rules P are going to look like S gives you, it can either give you this pair AB, and then you don't want to stop there. You want to keep going. You want to be able to continue producing. So ABS. And then suppose that you replaced S by ABS, then you might want to replace S by BA next. So then BAS. So I'm not really doing it in order, but you could also do AAS or BBS, right? So I have, these are the production rules that that actually do work in my grammar, that actually keep the string going. And then because I want at some point to finish the string, right? I don't want to keep producing. At some point I want to stop the production, then I'm going to end it off with a lambda, right? So then I can generate any string of even length, because what I can do is just produce the pairs from left to right, and then at the end replace with a lambda, right? So you could have done the same thing. So this is a right linear grammar. You could have done the same thing with a left linear grammar. You could have done SAA, SAB, SBA, and SBB, right? And lambda, right? So they would have both worked. Okay, so hopefully that's clear. If it's not, let me know. But now, so we've looked at a regular grammar. Now let's look at a grammar yeah. So that's that. So okay, actually that's a good point. Let me do that now. So this wasn't the only way of generating this language. So the other way is you could have kind of just done it. You can sort of think of what the FA would look like and kind of make your grammar do the same thing. So for instance, your FA, the FA that accepts this language, right, is this is my final state. Then if I see an A or a B, I go to a non-final state. And then if I see another A or a B, I go back to the final state. So the other thing you could have done, and we're going to talk about this in a second, is you could have said, my final state is S. I have another state A. And then I could have said I have S gives you AA, BA. So to go from S to A, I can either use an A or a B, or I could just stop and have a lambda. And then if I'm in A, then I don't allow a lambda, so I don't allow to have a terminal string from A. I just allow you to go back. I just allow you to go back, and this kind of reproduces the effect of accepting an even length string. Okay. So could we just define two variables? Yes. So the answer is yes. Okay. So that's for a regular grammar. Let's quickly look at a non-regular grammar. So here we have a grammar over, again, this, I don't know why there's an A here. It's only over the variable S. The terminal is AB, the start variable is S, and these are your production rules. Okay. So this production rule, easy to understand, it just gives you lambda. This one is maybe not as standard as so we haven't really seen a production rule like this before. So what this does, right, is you start with S, and then you substitute S with A and B, and then another S. Okay, and then if you continue to use this this variable, then at both sides of your S, you're going to have the same number of A's as you have B's, right? Because for every A you put, you're going to put a B, right? And you can keep going until you stop. And so what you'll have is you'll have a bunch of A's and then a bunch of B's, and the number of B's will be N. The number of A's will be N, and the number of B's will be N. So even though this grammar is linear, right? Because it's not, even though it's, sorry, I shouldn't have said that. Because this grammar, even though this grammar is linear, it doesn't mean that it's regular. Because for grammar to be regular, it needs to be linear, yes, but also right linear or left linear. So the fact that it's linear isn't enough. And it just so happens that it's not linear. And in fact, what it's going to do is it's going to produce a non-regular language. So you're going to see that this grammar here, this grammar G, L of G is actually going to be AN, BN, which you're definitely going to see tonight. And so this language is a very well-known language, and it's known not to be regular. So this is not regular, but we have a grammar that generates it. Okay, so all of this to say that you have to be very careful. The fact that something is linear doesn't necessarily mean that it's regular. You really need to be right linear and left linear. Okay, so yeah, that's what I want to say. Yes.
Sorry.
Yeah.
It is possible that if the grammar is not, it's either left linear nor right linear, but it's still regular, right?
It's possible for a grammar to not be regular, but to generate a regular language. So, for instance, was an example. Yeah, so if I have S gives you AA, right? This is not a regular grammar, right? Because it's not linear. But if I just say A gives you A, so if this is my grammar, then I could say, well, the only string that's generated by my grammar G is AA, right? So it's S gives you AA. Then I replace this first A with an A, and then this second A with another A. So the only string that's generated by this grammar is AA, right? So L of G is finite, meaning that it's regular, but this grammar here is not regular. So what that means is if a grammar is regular, then L of G is definitely regular. But if L of G is not regular, then it does not imply that G is not regular. Okay, this is very important. This is something that students often confuse. If a language is not regular, it doesn't mean that the grammar that, or no, sorry, it should be if it's regular. If the language that was generated by the grammar is regular, it does not mean that the grammar itself was regular. Okay, so I don't know if that answers the question. I feel like that was where you were heading.
Yeah.
Okay, good question.
But if I add a condition, say the grammar is an infinite grammar, so this will be true, right?
If the grammar is infinite but no, actually not necessarily. So let's say you have S gives you sorry, let's say A.
Oh, okay, I know, like
This is,
A, right?
if you have something like this, and then I mean, it doesn't.
So I mean
Yeah.
lowercase a and the S and the lowercase a.
Oh yeah, this is definitely. Oh well, actually, are you sure? So is this?
This is a regular language, right? This is a generic.
Yeah. This is a non-regular grammar, but it gives you a regular language.
Okay. Yeah. Thank you.
Okay. Good question. All right. So that was actually the exercise here. So this was a true/false question. So there are non-regular grammars that generate regular languages. So kind of already done it for you. I've shown you. Someone just gave an example, right? So this is an example of a non-regular grammar that generates a regular language. So I mean, what's the language? It's L of A star, right? So this is, so then asked like this, there are non-regular grammars that generate regular languages. So this is true, it's possible. Okay, okay. Next, what time is it? Okay. So what grammars generate the following languages? So this one, the language that contains the empty string, this one we've already done actually. So it's just S gives you a lambda. So, or in general, like just, if you just want, like, let's say your language is finite, right? So you have a finite number of strings, then it's very easy to find a regular grammar that generates the language. It could just be S gives you each of those strings, right? So, I mean, lambda is no different from that rule. Sigma star. So that one also we kind of did. Like I said, if, for instance, I had S gives me AS or BS or lambda, then this is enough to produce any language, any string over AV because at any given position, right? At any given position, if this is my string W, at any given position, I can either have an A or a B. And so here, what this is saying is that at any given position, I can either replace with an A or a B. Okay. What about this one? So what is a grammar that generates the empty set? Okay, that's not a valid. It's not a valid. Let's say it has to have a production role. It has to have a valid production role. Okay, nice, good, yeah. So exactly, yeah. So that's a possible one. You could have the production role S gives you S, right? This, so I mean, you can't do anything with this, right? You start at S, and then your derivation is S, right? So you can never. It's impossible. It's impossible to get a string of terminals, right? To get a string of terminals, let's say AB star, right? So that would be one example. It doesn't just need to be like this, right? It could be something like S gives you AS and BBS, right? So you're never going to be able to finish this production with a string, with only strings. You're always going to have a variable, right? So this would also would also generate the empty set. And yes, this is a regular grammar because it's both right linear and left linear. Okay, good. So that was for this section. I don't know if there are any outstanding questions about grammars. If not, we can go to the next section. Okay. All right, so it doesn't look like there are any questions. So the next section is actually also quick. It's basically, if you're given a grammar, and specifically it has to be a regular grammar, how can you go directly to an FA, right? So of course, what you could do is you could say, okay, I have the grammar, it generates a language, and then I create the FA for that. But is there a direct way of doing that? So very, very similar to what we did for regular expressions. And then, of course, the other way. So if I have an FA, can I easily create the corresponding or a corresponding regular grammar? This direction, these two directions are obviously not unique. So if you're given a regular grammar, there's several possible FAs which are equivalent to it, and the other way is also true, right? So there isn't a unique FA that maps to that grammar, and then vice versa. Okay, and so what is this actually going to be able? What is this going to allow me to do? So remember, I said that a language is regular if and only if, right? If and only if it's equal to a language generated by an FA, right? So to prove that a language is regular, the first method that we saw is, sorry, I said FA generates a language. That's very wrong. An FA never generates a language. So just let me point that out. But an FA accepts a language, right? So the first way to show that a language is regular was to create an FA, so either an NFA or DFA M, such that L of M, so the language accepted by M, is L. The second way that we saw on Monday was create a regular expression R, such that L of R is equal to L, so that the language denoted by R is L. Now the new third way that we've just seen actually, and that we're going to prove using this this logic, that the fact that if you have a regular grammar, then you can find an FA, and if you have an FA, you can get a regular grammar. So this new method of proving that a language is regular is you can create a regular, obviously a regular grammar, right? The fact that you found a non-regular grammar that produces a language doesn't tell you anything. So it doesn't tell you that it's regular. It doesn't tell you that it's non-regular. It doesn't tell you anything. So you need to actually, you have to absolutely find a regular grammar, G, such that the language generated by G is L. Okay. So, and these are actually the three ways, well, plus closure properties, but these are the main three ways that you can prove that a language is regular. Okay. So why is this third point true? Well, like I said before, it's because you can go from a grammar to an FA and vice versa, and that's what we're going to see. So if you're given an FAM, sorry, not an F, yeah, an FAM. So imagine you have, some initial state, you have a final state here, you have another state here, doesn't do very much. Okay. Then how can you convert this FA to an equivalent grammar? Well, the equivalent grammar, what you first need to know is that your start variable. So if you have the grammar G, which is a tuple of variables, terminals, start variable, and production rules. So the set of variables is going to be the set of states in your FA, M, so the set of states in M. Your set of terminals is going to be the alphabet over which M is defined. And your start variable is going to be the initial state of M, so it's going to be Q0. Okay? So that's the setup for your grammar. Next, how do you read transitions? So if you have a transition that looks like delta Q A gives you P, then you can convert this to Q gives you AP. So this is going to be your variable, and this is going to be your terminal. Right? No question? Someone unmuted themselves. Is there a question? No? Okay. So that's one possible production rule. The other production rule is you start at P and you actually don't read a symbol. You just have a lambda transition, and that gives you Q. Then this is related to the production rule P gives you Q. Okay. And the last thing is that if P is a final state, then what you do is you add the production rule P gives you lambda. Okay? So you have these three rules, okay? And with these three rules, it's possible to convert any FA to a regular, to a regular grammar. And specifically, it's always going to be, for this conversion algorithm, it's specifically always going to be a right linear grammar, right? Because your variable is always going to be on the right-hand side. On the rightmost element of the right-hand side. Okay, so let's see if this is clear by doing an example. And actually, well, the answer is, yeah, okay, maybe try not to look at the answer directly and try to do this yourself. I'll give you maybe 30 seconds. I feel like it's a pretty easy concept, so I'll give you 30 seconds to try it, and then we can look at it.
Sir, can you scroll down a little bit?
All right, so I feel like that was probably enough time for you to get it done. So let's just quickly look at the answer. I'll do it myself. So what did I say were the rules? So I said that you're given this FAM and you want to create a regular grammar, so specifically a right linear grammar. So your set of variables is going to be your set of states. So it's going to be Q0, Q1, Q2. Your set of terminals is going to be the set of the alphabet for your FA. So it's going to be, in this case, A, B, and C. So A, B, C. The start variable is going to be Q0, and you're going to have some production rules P. So what are going to be the production rules? Let's use a different color. Let's do blue. So let's start with Q0. So you have the variable Q0, and for all of the transitions, I'm going to use, right, Q0 isn't a final state, so I don't need to add a lambda. For all of the transitions, I'm just going to do the terminal for that transition and then the state, right? So Q0 reads an A, so Q0 writes an A and goes to Q2. The same thing for, let's say, C, right? So I can go to Q2 with C. And I can also go to Q1 with B. And here I have a lambda transition, so I can just write that I can actually go directly to Q2 without even the lambda. Okay, so that's for Q0. Then I can do the same thing for Q1. So if I'm in Q1, then well, I have sort of no choice but to write a C and to go to Q2. Okay. And the last one, Q2. So these weren't final states, so that's why I didn't add a lambda. But for Q2, Q2 is a final state, so immediately I'm already going to add a lambda. Then the only outgoing edge is this one. So I can say that Q2 goes to Q0. Okay, and is this the same? Yes, so that would be the equivalent regular grammar. And in this case, the equivalent right linear grammar. Okay. All right. So I feel like this is pretty straightforward. If there are any questions, just let me know. So what's the other way? The other way around is you're given a regular grammar. And again, in this case, we're going to look at right linear grammars. So for instance, I have S, A, S, B, A. A is, let's say A is let's say AA or A or lambda. Okay, so and I want to convert this to a FAM. So what are the states going to be for my FAM? So the states Q for my FAM are going to be the set of variables. Plus, I'm going to add an extra variable. I'm going to add an extra variable, an extra, state in M, which is going to, what do they call it? They call it, yeah, so let's call it the final state. So I'm going to create, because I want to make things easy, I want to create an FA that has a single final state. So this is going to be my set of states. Where the set of final states is just going to be, so this should be a set, so SF, okay. Then my initial state, Q0, is going to be obviously the start variable S. My alphabet is going to be T. And now the only thing that's really left is the transition. So how do the transition functions work? Oh yeah, so maybe, yeah, so quickly, I put a lambda here. You put lambda transitions, you put a lambda production whenever Q2 is a final state. So yeah, that's one. Okay, so for the transition, right, so what are the possible production rules I can have? So I can either have, for right linear grammar, I could either have A gives me B, A gives me some string B, and then A just, so let's say this is some string X over sigma star, and then A just gives me X, right? So if I just have A gives me B, then I can start at A and then just have a lambda transition to B, right? So this is a lambda transition. So this is for one. For the second one, if I have A, then some strings, and then B, what I do is I put a intermediary or intermediate intermediate state for each of the symbols of the string. So imagine X was, let's say, A, B, B. Then I could start at A, then I would read an A, go to an intermediate state, read a B, go to an intermediate state, read another B, and then go to, because after that there's B, I would go to B. Right, so this is my string X, and this is the variable B on the rightmost side, and this is the variable A on the left hand side. Okay, so that's how you would convert two. And then the last one, so X, so X can be anything, right? X can be lambda or any number of symbols in a row to make a string. So in that case, for 3, then that's where the extra state that I defined comes in handy. So if I'm in A and I have this production row X, then let's say X was A, B, then I put some intermediate state, and then my last transition is going to go to the final state SF. So that I only have a single final state, but because all of my production rows that give me only terminals go to final states, go to the single final state, then I'm conserving what I generate is the same as what I accept. Okay. So with this, that's the only thing I need to convert an FA to a regular grammar, and specifically to a right linear grammar. Okay. So so that's what we can do here. I'll give you another minute to try this one, because again, I think this is pretty straightforward. Yeah, so I'll give you a minute and then we'll look at it. So hopefully you're finishing up the FA. So we have this grammar G here, and we want to convert it to an FAM. So how do I do that? As I said, my initial state is going to be S, and I'm already going to add my final state SF, so that if I have any terminal or lambda productions, I can immediately make them go to, I can create a transition to the final state. So in this case, I have S. So what are the non-terminal production rows? So there's this one, and this one. So if I read an A, I can go to the state A. If I read a B, I can go to the state B. If I read a C, I can go to the state C. But if I read an A or a C or a B, I can also just go to the final state. That's it. Right? Okay, and I feel like that's basically the hardest part. Then you just have to repeat the same exercise for all of them. So for A, I can go to my final state with A or B. I can go back to A with an A, and I can go to B with a B. For the variable B, I can go back to B with a B, and I can go to my final state with a B. And then for C, I can stay at C with a C, go to B with a B, and then go to the final state with a C or a B. right? So clearly this is an NFA, right? It's obviously not a DFA. And in general, the conversion leads to an FA because you typically need some lambda transitions at some point, although we didn't need them here. Okay. So that's basically the conversion algorithm to and from. So notice here that in both directions of the conversion algorithm, we did right linear grammars. So yeah, so maybe an extra thing to sort of just an FYI. So everything's been with right linear grammars, but there's also an algorithm to go from right linear to left linear grammars and the other way around. So I think you've already seen this in lecture as well, but just to remind you of the steps, if you have a right linear grammar and you want to go to the left linear grammar, what are the steps? So actually, let's do it in an example. I wrote an example here. So let's have S gives me AS or BS or A, and then A gives me BAA or lambda. Okay, so I have this right linear grammar, and I want to convert it to a left linear grammar. There's a couple of steps actually that make it a bit tricky. But if you get the steps, then you should be good. So to go from right linear to left linear, the steps are what? So the first thing is you want to draw the FA. So let's do it in parallel. So I have S. From S, I can go to myself with A or B. And then I can go to A with a lambda. And then from A, I can go back to myself with BA. Or I can finish off with a lambda because I want a single final state. And I could just say lambda gives me, let's call the final state Z. Okay, so I draw my FA. And the second thing I want to do is I want to reverse the FA. So reverse my FA. So to reverse an FA, it's easy to reverse an FA if you only have a single final state. So what happens is your final state becomes the initial state. Your initial state becomes the final state. And all your transitions are reversed. Okay, so what does that mean? Let's do it in parallel. So 2, I reverse my FA. So my final state, which is Z, becomes my initial state. So this is my initial state. Then I reverse my transition to go from Z to lambda. From Z to A with lambda. Then I reverse also this transition so that to go to my intermediate state, I have to go read an A and then come back with a B. Okay. And then I can go from, now instead of going from S to A, I go from A to S with a lambda. And S becomes my final state. And well, in this case, reversing a loop always gives you the same loop. So I get this, right? So this is my reversed FA. The third step is to, from your FA, get a right linear grammar. So from the FA in 2, get the right linear grammar. Okay, so we just did that. So what's going to be the grammar? So in this case, my start variable is going to be Z. Then I can go from Z to A, right? That's the only production row I get. Then from A I can either go directly to S, or I can go back to myself with AB. So I can go back to myself with ABA. And then at S is a final state, right? So I can add a lambda. And I can also say that S gives me AS, and S gives me BS. Okay, so that's the third step. So really what's happened so far is I started with an FA, then I reversed my FA. So actually this is giving me the language reverse. Now I have the right linear grammar that gives me the language reverse. And so to get a left linear grammar that gives me L, all I need to do is reverse. So now I need to reverse. So I'm kind of reversing the reverse. So I'm reversing the right linear grammar to a left linear grammar. Okay. And what I mean by reverse is just reversing the production rules. So this is still going to be my start variable. So Z gives me A gives me S. That doesn't reverse, right? You're not flipping anything for a single thing. But for A is going to go. So you're basically flipping like a mirror image. So A is going to go in front. Then I have BA. And then S gives me lambda. S gives me SA, and S gives me SB. And so this is a left linear grammar that's going to generate the exact same language as this guy. Okay, and that's how you go from right linear to left linear, and from left linear to right linear is the same idea, except that you start by reversing. So let me write it. I won't do an example, but from left linear to right linear, the idea is one, you reverse the left linear grammar to a right linear grammar. Then you convert to an FA. Then you convert the FA to a, you reverse the FA, right? You reverse the FA, right? So this is one reverse, and this is another reverse. So two reverses gives the same thing. And so then the only thing you need to do is convert the FA, so convert the FA to a right linear grammar, okay? And that's how you do both directions. So you probably saw some of this in lecture, but this is just, it's good to know that this exists. And if you ever have a question where you need to know what the left linear grammar is, then you can use the conversion algorithm. Okay, so I think, yeah, so that's about it in terms of content. I don't know if there were any questions. Really, no questions?
Sorry.
Yeah.
What Zoom link will you use for the midterm review section?
I will use the same one as the tutorial.
Yeah, but there are two tutorial sections. So one.
My tutorial section.
Okay.
Good.
Okay, thank you.
Yeah, no problem. Okay, good. So maybe when is the review? Also I need to check with the professor. I need to check with the professor if I can do a review. He'll probably say yes. So I said Friday from 4 to 5, and I'm going to record it. Maybe one last thing, actually. I had said on Monday that assignment 1 was really well done. I think I said that, well, it was still really well done. The average is high, but I did that before I corrected the last question, which a lot of people had a lot of trouble with. Let me just look at, I'm going to try to, yeah, so it was, you needed to find a DFA for ANBM. Yeah, so it was find an FA for the language ANBM, and command is greater or equal to 0, and and n is not equal to 1, or m is not equal to 1. Okay, so this was Yeah, so this was really not well done. A lot of people, the majority, like I think half of the assignments I marked, I made this mistake where you started the DFA and none of these first three states were final. So basically you're saying that A was not accepted, B was not accepted, and lambda was not accepted. Okay, and that's just because you, well, for the majority of people, I think that's because they didn't really understand what they didn't understand what this condition meant, right? So if you just use De Morgan's law, right? So remember, what's De Morgan's law? It's if you have not x and y is equal to not x or not y, then it becomes a lot clearer what this is saying. This is saying that you cannot have n is equal to 1 and m is equal to 1. Okay, so this language definition, okay, is just saying that you can have any string, a n, b, m, where you have any number of a's followed by any number of b's, except for ab. That's it. That's the only string that isn't in L. Okay, so a lot of people thought it can't be any string that has a single A, and it can't be any string that has a single B, right? That's not right. That's not how you read the language. So be very careful when you read set notation. So this was actually equal to just L of A star, B star minus AB. So this was the same. That was the trap in the assignment. And so just make sure that you don't fall into a similar trap in the midterm, because you just needed to do this manipulation for it to be clear. Okay, so
so
yeah.
Sorry.
Yeah.
So what you're saying is you could have one B as long as there isn't just one A, or vice versa. That's what
you can have. Yeah. Okay, you can. Yeah.
So it would have only if, yeah, like you said, just AB basically, but you could have A, BB, or BB.
Yeah, because this is saying, right? It's saying keep the string if n is not 1 or m is not 1, right? So like you could just say, if you had a for loop n in, let's say, 1 to 100, and for m in 1 to 100, then if n is not equal to 1 or m is not equal to 1, keep n comma m. Then I think it's clear that the only thing you're not going to keep is when n is equal to 1 and m is equal to 1. Right?
Right, yeah.
So that was just something to be mindful of. But other than that, it was very well done. So I'm happy. All right. So it doesn't look like there are any more questions though. So I'll let you guys take a break. I will confirm with the professor if a midterm review is allowed, and I'll send a Moodle with the information, sort of probably by this evening or tomorrow morning. Okay. So take care, everyone, and have a nice lecture. All right. Bye-bye.